Okay, this is the problem that we started in the previous segment. It's the same structure that we had before. The only difference is that the nodes and elements are labeled differently. Kind of have done it in a random way. So we still have to loop through the elements, and we're going to do that in a minute. All right. So element number one, I've drawn it here for you on the right side. Okay, and the only thing I'm going to do is I'm going to put a superscript 1 on top of the masses, because this is to emphasize that these are coming from element number 1, and a superscript 1 on top of the forces to emphasize that they're coming from same element number 1. So how's the equation of the motion? It's very straightforward. It's M1, M1L, M1R, and a 0 and a 0. XR, XL double dot, XR double dot, plus the stiffness, K1 minus K1 minus K1 and K1 times the displacements, XL, XR, equal to FL1 and FR1. So these are supposed to go in the proper positions in the global stiffness matrix and the mass matrix. So actually, let me write those global equations here for you. Okay, so what's the easiest way of deciding on where to put things? All right. So notice that when you look at element number 1, it goes between node number 1 and node number 3. So when we try to put these things, I put a reference global here, 1 and 3, 1 and 3. So that number is going to go into row 1, column 1, M1L. This number is going to go row 1, column 3, row 3, column 1, and row 3, column 3. Okay, same thing with the stiffnesses. So it's going to go into K1 minus K1 minus K1, K1. Same thing with the load. This is going to go into row 1 on the right side, and this is going to go into row 3. So it's going to be F1R. All right, now we have to go to element number 2, and since it's going to be this matrix that we're going to be using, why don't I go and do a copy and paste here? Paste it. Okay, and now we are going to element number 2. Element number 2. So let's draw that for the sake of completeness. ML from element 2, MR from element 2, this is FR2, and this is FL2. Okay? And this is element number 2. And keep in mind that this element, when you look at your connectivity from the original diagram, it runs between node 5 and node 4. Okay, good. So what's the equation of motion? Well, it's M2L 0, 0, M2R, accelerations, the stiffness, K2 minus K2 minus K2, K2, times displacement, equal to the right-hand side, FL2 and FR2. And to decide where they're going to go, we use this connectivity. So this is 5 and this is 4. This is 5 and this is 4. Okay? And let's now put it in the proper place. Now put it in the proper place in this matrix. All right. So that number goes into row 5, column 5, which means I have to scroll down a little bit more here. Row 5, column 5, so it's going to be M2L. This is going to go into row 5, column 4, which is here. That's going to go to row 4, column 5, which is there. And this is row 4, column 4. M2R. For stiffnesses, row 5, column 5, row 5, column 4, row 4, column 5, and row 4, column 4. That's going to go into row 5, and this is going to go into row 4. All right. Once again, let's do a quick cut and paste here. All right, good. Okay, so we now go to element number 3. Element 3, let's draw that. This is ML3, MR3. This is element 3, stiffness 3, of course. This is FL3, and here is FR3. Okay, what's the equation of the motion? Well, equation of motion is ML300 MR3 XL double dot XR double dot plus K3 minus K3 minus K3 K3 XL XR equal to FL3 and FR3. And keep in mind that when you look at your original drawing, the nodes that go with node number with element number 3 are running between node 4 and node 2. So in order to put these in the right place, we have to, it's easy to put a, makes it a lot easier if you put these 4 and 2 there. So that number goes into row 4, column 4, and latches on to what's already there. Plus M3L. This goes to row 4, column 2. Row 4, column 2. That goes to row 2, column 4. And this goes into row 2, column 2, and latches on. M3R. Stiffnesses. This goes to row 4, column 4. It's going to be plus K3. This goes to row 4, column 2. Row 4, column 2 minus K3. Row 2, column 4 minus K3. And row 2, column 2. So it's going to be K3. For load vector, this is going to go into row 4, F3L. And this is going to go into row 2, Okay, the final thing we have to do is the final thing we need to do is to go to element number 4 and do this, repeat this. So just have to copy, paste. All right. So now we go to element 4. Move this thing out of the way. Element 4. Let's draw that. Element 4. M left 4. M R4. This is F L4. This is FR4. Equation of motion, ML4, 0, 0, MR4. Acceleration, XL double dot, XR double dot. Stiffness, K4 minus K4 minus K4, K4. XL, XR. FL4, FR4. So you have to put these in the right spots. So let's see now. Node element number 4 runs between nodes 3 and 5. This is 3 and 5. So let's put the 3 and 5 here. 3 and 5. That means this number goes and latches on to row 3, column row 3, column 3. Now I think what I copied and pasted doesn't have all the stuff in it. So let me go there and just put it in here. Just bear with me for a second. I've done this thing so many times. I don't want to lose it again. So let me see now. Okay. I do have to do a little bit of cleanup here. Just be patient, please. So this stuff I don't want. I can delete. Yeah, good. Oh. You know what? What I'm going to do is I'm going to cross this stuff out to garbage. Okay. And now put these things in the right spots. Okay. So M4L. This is going to go into row 3, column 3. So let's see, row 3, column 3. It's going to be right here, plus M3L. And then that's going to go into row 3, column 5. So it's going to be plus, it's going to be a 0 here. Row 5, column 3, so it's going to be a 0 here. Yeah. And this is going to go into row 5, column 5, plus M4 R. Okay, this is going to go into row 3, column 3. Sorry, row 4, row 3, column 3, K4. This is going to go into row 3, column 5. Row 3, column 5. So minus K4. This is going to go to minus K4. And finally, row 5, column 5, which is going to be plus K4. All right, that fellow is going to go into row 3 plus F4 left 1. And this is going to go into row 5 plus F4 right 1. All right, that's good. Okay, so let's see what we exactly know. Node 1 and node 2 are fixed. So this is going to be 0. And the acceleration of it is 0 because the node is fixed. This is 0 and this is 0. This is the reaction force at node 1. This is the reaction force at node 2. Left wall, right wall. What about this? This is coming from elements 1 and 4, right side of element 1, left side of element 4. This is the applied force. That's given. What about the one down below it? It's coming from elements 2 and 3. Just look at your drawing, elements 2 and 3. Left node of element 3 and right node of element 2. And this is 0. There is no external force applied there. And so is this one. This is 0. All right, so let's go to masses now. Remember, this is, we can think about it as being 0 because this is at the wall. And we can think this as being 0. Because this is referring to element 3, which is the extreme, the element or the spring at the extreme right end and the right end of it, which is the wall. So if we concentrate only on the reduced equation, this is the stuff that we've got. We have this and that. So I'm going to write these equations, the reduced form, for you. So the reduced equation of motion V/3, that thing is just the mass at node 3. This is just M3, 0, 0. This is just the mass at node 4. If you look at it, I assume that it's M4. And this is M5. Times the acceleration, x2 double dot, x3 double dot, x4 double dot, x5 double dot, plus the stiffnesses. Whatever they happen to be, just this piece. So it's going to be K1 plus K4, 0 minus K4, 0, K2 plus K3, minus K2, minus K4, minus K2, and K2 plus K4. 3/3 matrix, you can see like that. Times the displacements equal to big F 0, 0. So just like in the previous case with the other labeling of the node, let me see. Let me go to the next page. Just like in the previous case, you basically have a system of equations to solve, system of differential equations to solve in time. A 3/3 matrix, mass matrix, times the acceleration vector, plus the stiffness matrix, times displacement vector equal to a global load vector. Global load. However, the structure of this K is different with the original label. And you might say that what difference does it make? Notice that as far as we and the end user is concerned, there is no difference. However, from practical point of view, implementation point of view, the bandwidth of this matrix K is critical, and it has to be as small as possible. Notice that by relabeling it the way we have done, we have increased the bandwidth. It may not be quite obvious in this problem, and in fact it is not. The bandwidth is the same here. But if you had more elements, you would have seen that by randomly, just assigning nodes and elements, the bandwidth can dramatically increase. All right. So, by the way, if we assume that the masses M3, M4, M5, or let's hypothetically say 1,000, I don't know, give some numbers here. Let's say 1 kilogram. And the stiffnesses, all the stiffnesses are the same. K1 equal to K2 equal to K3 equal to K4. And let's say it's equal to, I don't know, 10,000 or 100,000 Newton per meter. Okay. And the actual applied force is equal to 1,000 Newton, then the equation that needs to be solved in time looks like this. This is 200,000, 2 times 10 to the 5, and there's a 0, there's a minus 10 to the 5, there's a minus 10 to the 5, there's a 0, 2 times 10 to the 5, minus 10 to the 5, minus 10 to the 5, 0. Something wrong here. Actually, this is minus. Let me see. I don't want to make a mistake here. Just 1 second. Sorry. This is a mistake here. This is minus 10 to the 5. And this is also 2 times 10 to the 5. Oh, something is wrong here then. Just bear with me for a second. No, that's okay. That's okay. Times x3, x4, x5 equal to 1,000, 0, 0. This equation has to be integrated in time, and once the initial condition is specified, and you're going to get your x3, x4, x5, and substitute in the first two rows to get your reaction forces at the wall. I have one more segment on this topic, basic FEAs, and then at least that'll take care of whatever I wanted to do in the two lectures that I'm missing.